I'm Nova, and this is OpenClaw Daily. Today starts with OpenClaw v 2026.5.4. It also includes OpenClaw v 2026.5.5 and OpenClaw v 2026.5.6. The important change is not a slogan. It is a set of operator fixes around real-time voice, Codex OAuth routing, Discord and Telegram progress, channel session routing, guarded fetch timeouts, model auth inspection, SecretRef resolution, and gateway diagnostics. If an agent is going to live in chat, meetings, voice calls, browser tools, and long-running jobs, these are the surfaces that decide whether it feels dependable.
I'm Alloy. The release sequence has 3 layers. The first release makes the voice and extension contract pieces more operable. The second tightens channel behavior, progress drafts, control UI sessions, XAI reasoning controls, approval delivery, media completion handling, and gateway status. The latest hotfix fixes the sharpest regression. Valid OpenAI Codex /GPT 5.5 OAuth routes could be rewritten into OpenAI /GPT 5.5 API key routes by Dr. Repair, which is exactly the wrong move for an OAuth-only codex setup.
The recovery path is deliberately concrete. If the default model was moved to the direct OpenAI route, switch it back to OpenAI Codex /GPT 5.5, validate the config, and confirm the auth profile is the Codex OAuth profile rather than a missing OpenAI_API_key dependency. The distinction matters because the model name may look almost identical while the credential path is completely different. One uses ChatGPT or Codex OAuth, the other expects a raw OpenAI API key on the gateway.
That one fix explains a lot of real breakage. A gateway can be authenticated, the user can have a valid Codex OAuth session, and the agent can still fail if configuration points at the API key provider family. The useful diagnostic is not just, does GPT 5.5 exist? It is, which provider namespace owns the route, and which auth profile resolves for that namespace. The hotfix turns that from a confusing missing key loop into a specific recovery action.
Start with the big capability change. An agent can join a Google Meet through a Twilio dial-in path and speak through the real-time Gemini voice bridge instead of falling back into a conventional phone prompt. That means the phone leg, the meeting room, the model audio stream, and the runtime queue now have to behave like one low-latency system.
Here is the operator version. To set this up, enable the voice call or meet path, configure a Twilio Media WebSocket route for the dial-in leg, choose a real-time capable Gemini model and voice in the agent profile, and point the meet join workflow at that voice backend. The release matters because provider voice and model overrides are now honored in telephony synthesis, so speech logs should match the backend that actually produced the audio. The first new capability is a real phone-to-meeting voice agent. Before, a dial-in bridge could be demoable but brittle, generated audio might outrun the WebSocket, barge-in could leave stale speech waiting in a queue, and fallback speech could hide the fact that the real-time path had stopped being real-time. Now the paced audio stream has bounded buffering, overload closure, and interruption clearing.
Bounded buffering is the core technical change. Real-time voice has 3 clocks: incoming human speech, generated model audio, and the transport's ability to send frames. If generated audio arrives faster than the WebSocket can transmit it, the runtime has to buffer. If that buffer is unbounded, the user hears old answers after the conversation has already moved on. This release closes overloaded real-time streams before stale provider audio can accumulate indefinitely.
Barge-in is the second capability. A participant can interrupt the agent, and the runtime clears pending generated audio instead of merely pausing playback. That is important because interruption is a state boundary. Once the user interrupts, the old answer is no longer valid. Any audio still queued behind the transport belongs to the old turn, so clearing it is part of correctness, not just user experience polish.
The third capability is honest failure on the real-time path. Conventional CML prompts are useful in ordinary telephony flows, but they are not a substitute for a real-time model bridge. If a live model call silently falls back to CML, operators may think the real-time system is healthy while the user is hearing delayed or mismatched speech. The release keeps real-time speech on the real-time bridge so failures are visible and diagnosable.
The practical test is straightforward. Run a Meet dial-in session, speak over the agent while it is answering, and check that the old answer does not continue after the interruption. Then deliberately create slow send conditions or a bursty provider response and confirm that the stream fails visibly instead of building a long delayed speech backlog. A voice agent that cannot pass those tests will feel haunted in production.
The next improvement is credential and channel setup reliability. SecretRef contract resolution now works for external channel extension packages whose compiled artifacts live under a distribution folder. Before this fix, a channel could be configured with an environment-backed Discord token reference and still appear unconfigured at gateway start because the runtime did not find the package's secret contract sidecar in the compiled location.
What this means for your agent is that external channel packages can be installed and still contribute the metadata needed to resolve their secrets. The setup pattern is: install the channel extension, keep credentials as SecretRef entries instead of plaintext, start the gateway, and let the runtime load the compiled contract metadata into its snapshot. If the contract is present, the channel should validate without exposing the token.
Secret Supply also preserves auth profile keyref and tokenref fields while scrubbing provider target secret material. That gives operators a safer repair loop. You can remove plaintext from a config while keeping the reference graph that says where the credential belongs. Without that, a cleanup step can accidentally turn a secure configuration into an unusable one.
The visible new ability is safer credential inspection. The model auth list command can show saved per provider or per agent auth profiles, with provider filtering and JSON output, without printing secret values. That is exactly what you want when an agent can call multiple model providers. You need to know which profile exists, which agent scope uses it, and whether the runtime sees it, but you do not want tokens dumped into a terminal or chat log.
The setup is operational rather than glamorous. Store provider credentials through the auth profile mechanism, reference them by key, then use the auth listing surface to verify presence and scope. If a model call fails, first check whether the intended profile exists and whether the agent is using that profile. That is faster and safer than opening raw config files or triggering test calls that may leak cost and noise.
D2026.5.5 extends the channel story before extension installation. Discord heartbeat ACK timeouts are measured from the actual heartbeat send, which prevents late initial heartbeats from being treated as false reconnect failures while the channel is still awaiting readiness. Discord plain text control commands such as /steer now go through the normal authorization and mention gate instead of being silently dropped before an agent session can see them. Telegram and Codex progress drafts also stop duplicating native tool progress, so message tool only status stays visible without making every tool appear twice.
The same release tightens a handful of other operator paths. Matrix approvals retry transient send failures instead of stranding a pending approval prompt. Slack reconnect logs preserve structured SDK and API context instead of collapsing to an unknown error. The control UI keeps chat and channel tabs responsive while history payloads or channel probes are slow, labels partial channel status, and records slow render timing in the event log. Those are not decorative changes. They make remote agent control easier to debug while the system is under load.
D2026.5.6 adds fetch path cleanup on top of that. Plugin runtime fetch drops third-party symbol metadata from plain request headers before passing them into native fetch or headers, and the debug proxy normalizes captured header dictionaries before replay. Guarded web fetch also bounds dispatcher cleanup after request timeouts, so timed-out fetches return tool errors instead of leaving gateway tool lanes active. For an agent that browses, calls plugins, and proxies requests, that is the difference between a clean tool failure and a lane that looks alive while nothing useful is happening.
Extension installation also gets less fragile. When configuration references an official external extension that is not installed, the runtime can emit catalog-backed install hints instead of telling the operator to delete valid configuration. That changes upgrade behavior. A missing package is treated as an installation problem, not proof that the config is junk. There is a setup lesson there too. Keep official channel and tool extensions declared in the runtime configuration, then let catalog-backed hints guide the missing install step after an upgrade or migration. The old failure mode was confusing. The agent could have the right root and the right secret reference, but a missing package made the whole surface look invalid. The new path tells you what to install.
Workspace scoped metadata snapshots are the performance improvement behind several operator surfaces. Compaction, embedded run model generation, PDF model setup, model catalog readers, and manifest contract readers can reuse the current workspace-compatible metadata snapshot instead of forcing cold scans. The promise is not blind caching. The snapshot is used when environment, config, and workspace compatibility checks say it is safe.
What becomes easier is running agents with many optional surfaces, chat channels, media tools, browser control, memory, model providers, cron, and external packages. The runtime should not rediscover every manifest and contract on every hot path. After this release, more of those paths can reuse a validated snapshot, reducing startup and control plane latency while still falling back to discovery when compatibility changes.
Active memory gets a small but important guard. Session store channel entries containing a colon are skipped when resolving the recall subagent's channel, so scoped conversation IDs do not get misread as bundled extension directory names. That matters because chat systems often encode scope inside identifiers. An identifier can be valid for a conversation and invalid for a package directory at the same time.
The practical result is fewer recall crashes in scoped channels. If your agent uses memory across chat contexts, the runtime now has a better boundary between conversation identity and extension package identity. That makes memory recall safer in multi-channel deployments where IDs are not simple folder-like names.
Progress reporting is the next major operator improvement. Slack can render richer progress drafts from structured progress line data, keep the newest rich progress lines when block kit limits force trimming, and cap long tool lines so the draft does not jump around on every update. Compact explain mode summaries are also the default for verbose and progress views, with raw detail available when you explicitly ask for it.
This changes what you can ask an agent to do in chat. You can start longer work and expect the progress surface to preserve the newest useful status instead of becoming a wall of wrapped logs. For setup, choose the default compact progress mode for normal channels, then raise tool progress detail only for debugging agents or specialist sessions. The chat surface should show state, not every byte of tool output.
Subagent result preservation also improves. When direct completion fallback bypasses the usual requester agent announcement turn, every grouped child result is still preserved. In plain language, if you delegate work to several child agents and the runtime uses a fallback completion path, the child outputs should not disappear just because the announcement route changed.
That unlocks more reliable delegation. A parent agent can split research, testing, or implementation work across children and still receive the grouped results even if the normal announce turn is skipped. The operator should judge this by the final result bundle. Did every child report survive, and can the requester agent still synthesize from all of them?
Startup diagnostics are more explicit. Gateway startup now records phase spans, active work labels, stale terminal bridge markers, and default sync-I/O tracing in watch mode. It also defers non-readiness sidecars until after the ready signal, avoids hotpath channel package barrel imports, fastpaths trusted bundled metadata, and avoids loading a source transform path when native loading is enough.
The immediate capability is diagnosis. If startup is slow, you can look for the phase that owns the time, metadata discovery, channel setup, sidecar loading, readiness work, or a stale bridge. Without phase spans, startup complaints turn into guesswork. With spans, you have a map of where to optimize or where to file the bug.
Windows gets a concrete gateway fix as well. The default loopback listener binds to 127.0.0.1 on Windows, so dual stack localhost behavior around the IPv6 loopback cannot wedge local HTTP requests. This matters because local agent control often depends on the browser, gateway, and command line tools agreeing on the loopback route.
The setup guidance is simple. On Windows, use the default local gateway binding unless you have a deliberate reason to expose another interface. If local HTTP calls were failing because clients disagreed over IPv4 and IPv6 loopback, this release removes one of the obvious traps.
Put together, the improved runtime gives an agent 7 practical upgrades. It can speak in a live meet dial-in with bounded real-time audio behavior. It can keep Codex OAuth GPT 5.5 routed through the codex provider instead of the API key provider. It can use external channel packages without losing their secret contracts. It can inspect model auth profiles without leaking secrets. It can show compact, structured progress during long work. It can return clean timeout errors from guarded fetches. And it can explain slow startup with phase-level evidence instead of folklore.
The setup sequence I would use is deliberately boring. First, upgrade the runtime and restart the gateway so the readiness path and startup spans are from the new build. Second, verify model authentication with the auth listing surface before running any expensive model calls. Third, verify the channel extension package is installed and that its SecretRef contract is visible at gateway start. Fourth, start a small chat job and inspect compact progress. Fifth, only then test the real-time meet dial-in path.
For the meet path, keep the test mechanical. Start a meeting join through the voice call route, confirm the selected real-time model and voice show up in the speech logs, speak while the agent is answering, and listen for immediate stop behavior. Then run a longer answer and watch for delayed speech. If the queue is overloaded, the correct behavior is a visible stream close, not a 2-minute ghost monologue from an old turn.
For SecretRefs, the success condition is also mechanical. A channel credential should remain referenced by key, not pasted into config. The apply or scrub path should remove secret material while preserving keyref and tokenref metadata. Gateway startup should resolve the channel package's compiled contract metadata and mark the channel configured. If any one of those steps fails, you now have a narrower place to look.
For progress, treat the chat draft as an operator dashboard with a very small budget. It should tell you the current phase, the most recent useful tool line, and whether the work is still alive. It should not paste every raw log line into the channel. When you need raw output, increase tool progress detail for the debugging agent or session, not for every normal user-facing workflow.
For delegation, test with 2 or 3 child agents and make sure the grouped results survive even when the direct completion fallback path is used. A multi-agent system is only useful if the parent can trust that child outputs are preserved across routing changes. Otherwise, delegation silently becomes sampling. Maybe the parent saw all the work, maybe it did not.
For startup, compare what operators used to do with what they can do now. The old loop was restart, wait, guess, open logs, guess again. The new loop should be restart, inspect phase spans, identify whether the time belongs to discovery, channel setup, sidecars, readiness, or terminal bridge state, then fix the owning phase. That is a real improvement because it turns a vague slow start complaint into a targeted bug report or config change.
The testing checklist is equally concrete. For voice, test interruption and overloaded audio sends. For credentials, start the gateway with SecretRef-backed channels and verify they configure without plaintext. For metadata, compare hot path latency after the workspace snapshot is warm. For progress, run a long tool job in Slack and confirm the newest status survives trimming. For startup, inspect phase spans before guessing.
That is the release verdict. This is an operations release. It is not trying to sell magic. It makes real-time speech, secrets, external packages, model auth, progress, delegation, and startup easier to operate, with setup paths and failure checks operators can actually repeat. Now we can move into the outside stories, graph runtime control first, then inference serving stabilization.
LangGraph version 1.2 alpha turns long-running agent graphs into timeout, recovery, checkpoint, and streaming problems. LangGraph version 1.2 alpha is a workflow runtime release. The important part is not that graphs can call models, it is that long-running graphs need execution limits, recovery paths, checkpoint efficiency, and streaming projection. When an agent workflow has multiple nodes, slow tools, external APIs, retries, human interrupts, and long message history, The runtime needs more than a loop and a state object.
Per-node timeouts are the clearest example. LangGraph adds timeout equals on add_node, with a timeout policy that can set run_timeout, idle_timeout, or both. A hard run timeout aborts after a wall clock limit regardless of progress. An idle timeout resets when progress is yielded and aborts when a streaming node stops producing output. That distinction matters for agent tools. A model call, browser run, or external API stream may legitimately take time, but a silent hang should not hold the graph forever.
Timeouts apply to async nodes only, and sync nodes with timeout are rejected at compile time. That is a good constraint because Python cannot safely interrupt arbitrary synchronous work in the same way it can manage async progress. The release also supports heartbeat-style yields. An async node can yield an empty update to reset the idle clock without writing meaningful state. That gives developers a way to say, this tool is still alive, while keeping the graph state clean.
When a timeout fires, LangGraph raises node timeout error, clears any writes from that attempt, and hands off to retry policy. Clearing writes is the subtle but important part. If a node times out halfway through an operation, partial writes can corrupt the graph state. The runtime should either commit a coherent result or treat the attempt as failed. Then retries and recovery handlers can decide what to do next.
Node-level error handlers add the recovery path after retries are exhausted. An error_handler receives a typed node error with the failing node name and exception, and can return a command that updates state and routes to another node. This is useful for saga-style compensation patterns. If payment capture fails after retries, update the state to compensated and route to finalize. If document parsing fails, record the parse error and route to a fallback summarizer. If a browser action fails, mark the page state and switch to a screenshot audit path.
The runtime design here is explicit. Retry handles transient failure. Error handler handles exhausted failure. Command handles state update and route selection. Interrupts bypass the handler, which matters because a human or system interrupt should not be disguised as an ordinary tool failure. That separation keeps operational semantics understandable.
Delta channel addresses checkpoint overhead. In long-running threads, channels such as message lists grow over time. Without a delta mechanism, every checkpoint can reserialize the full accumulated value. Delta channel stores only the incremental delta at each step and writes a full snapshot every configured number of steps through snapshot_frequency. That changes the cost model. Writes become cheaper for growing channels, while reads may need to reconstruct from deltas until the next snapshot. The tuning question is how often to snapshot so replay latency stays bounded without returning to full-value checkpoint bloat.
This is directly relevant to agent systems because message histories, tool traces, event lists, and observations can grow quickly. If each checkpoint writes the entire history, durable execution gets more expensive the longer the conversation runs. Delta-based checkpointing makes long threads more practical, but it requires reducers that correctly merge batches of writes. A bad reducer can lose ordering or duplicate messages. The episode should explain that Delta Channel is a storage contract, not just a performance flag.
The streaming API also moves toward content blocks and typed per-channel projections. That matters because modern agent UIs do not only stream text. They stream tool calls, intermediate reasoning summaries, progress events, generated artifacts, state updates, and final messages. A streaming API that can project typed content per channel gives clients a cleaner way to render the right thing in the right place. It also helps avoid mixing internal state updates with user-visible answer text.
Graceful shutdown belongs in the same discussion. Long-running graph runtimes need to stop without corrupting checkpoints or leaving tools in unknown states. Shutdown interacts with timeouts, retries, checkpoints, and streaming. If a process receives a shutdown signal while a node is mid-attempt, the runtime has to decide what is committed, what is retried later, and what is surfaced to the user. LangGraph version 1.2 alpha is interesting because it treats these as first-class runtime concerns.
The practical rating for builders is high if they run durable workflows, multinode agents, or UI-facing graph streams. Timeouts prevent invisible hangs. Error handlers make fallback explicit. Delta channel reduces checkpoint pressure. Typed streaming improves front-end rendering. The trade-off is that every new control surface needs policy, timeout defaults, retry limits, snapshot frequency, compensation routes, and stream visibility rules.
The setup implication is that a graph definition should stop treating failure policy as an afterthought. Put timeout policy next to the node that owns the risk. A browser node may need an idle timeout because it should keep yielding progress. A payment or write side effect node may need a shorter run timeout and a specific compensation route. A summarization node may need retries but no compensation because it has no external side effect. Different nodes deserve different operational contracts.
Delta channel also needs a test before production. Feed the reducer several batches of messages, tool events, and state updates, then reconstruct from deltas and compare the result with the full expected value. That catches ordering bugs and duplicate write bugs early. A smaller checkpoint is only a win if recovery gives the same graph state the full checkpoint would have given.
For UI streaming, the client should be tested with mixed content, normal text, tool call blocks, progress events, and final state updates. The point of typed projection is that the transcript, progress panel, and debug inspector do not receive the same undifferentiated stream. If the front end collapses those streams back into one text box, the runtime improvement is wasted. vLLM version 0.20.1 makes DeepSeek v4 serving a kernel, communication, cache, and tool call reliability story. vLLM version 0.20.1 is a patch release, but it is exactly the kind of patch release inference operators should care about. It focuses on DeepSeek v4 stabilization and performance improvements after initial support landed in version 0.20.0. That distinction matters. Initial support means the model path exists. Production serving means kernels, communication paths, cache behavior, structured output, tool calls, CUDA graphs, and memory checks are stable under load.
The DeepSeek v4 work starts with base model support and multistream pre-attention GEMM. GMM is the matrix multiply workhorse of inference, and pre-attention computation can become a bottleneck depending on batch shape and model architecture. Multistream execution tries to overlap or schedule parts of that work more effectively. vLLM adds a configurable pre-attention GEMM knob and tunes the default vLLM_multi_stream_GEMM_token_threshold, which tells operators that the optimization is workload sensitive. Thresholds matter because the right setting for small batches may not be right for large token loads.
All-to-all communication support for BF16 and MXFP8 through FlashInfer one-sided communication points to the distributed MO problem. Expert-style models need tokens routed across devices. All-to-all communication is expensive, and low-precision formats reduce bandwidth and memory pressure, but they introduce compatibility and numerical concerns. Supporting BF16 and MXFP8 means the serving stack is trying to keep the communication path aligned with the model's precision and performance profile.
The FP32 to FP4 conversion optimization is another serving-level detail. Low-bit inference can save memory and bandwidth, but conversion overhead can erase some of the win if it is too slow. A PTX CVT instruction for faster FP32 to FP4 conversion moves that cost closer to the hardware path. This is the kind of kernel work that users do not see directly, but it changes throughput and latency at scale.
Integrated tile kernels for optimized head computation continue the same pattern. Attention and head computation are not abstract math in production, they become tile sizes, memory layouts, hardware occupancy, and synchronization costs. A release note about head_compute_mix_kernel tells operators that model support is being tuned below the Python API layer. That is where many large model serving gains actually come from.
The bug fixes are just as important as the performance work. vLLM fixes a persistent TopK cooperative deadlock at TopK 1024 and an inter-CTA initialization race on Radix Rostate, with temporary persistent TopK disabling as a workaround. Deadlocks and interblock races are dangerous because they may only appear at certain batch sizes, model paths, or GPU schedules. An inference server can look healthy in small tests and then hang under a particular production shape. The safe operator response is to treat these fixes as stability prerequisites, not optional performance polish.
AOD compile cache loading, torch inductor errors, and repeated rope cache initialization also get fixes. These are deployment friction points. Ahead of time compile caches are supposed to reduce startup or warm-up cost, but a cache loading import error can block serving entirely. Torch compiler errors can appear only under specific graph or kernel paths. Repeated rope cache initialization wastes work and can create latency spikes. Stable inference is a chain of these small pieces working together.
Tool call behavior gets a notable repair, missing type conversion for non-streaming tool calls in DeepSeek version 3.2 and v4. That matters for agent systems. A model can be fast and still be unusable for agents if structured outputs or tool calls break in one response mode. Non-streaming and streaming paths often have different parsers and conversion points. Operators need both to work if they support batch evaluation, synchronous API calls, and streaming chat.
General vLLM fixes reinforce the same production theme. max_number_batched_token is captured in CUDA graph state. number_GPU_blocks_override is accounted for in max model length checks. Expandable segments are auto-disabled around the CUMM memory pool. Reasoning parser quarks are passed to structured output. ROCM paths for quark W4A8 GPTOSS get argument fixes. These are not headline features, but they prevent mismatches between configuration, graph capture, memory allocation, parser behavior, and hardware backend.
The DeepSeek v4 part of the vLLM release is a reminder that model serving is a systems problem before it is a product feature. A model path can load, answer a test prompt, and still fail under real serving pressure. The pressure arrives through batch shape, expert routing, graph capture, memory pool behavior, parser modes, and tool call envelopes.
Multi-stream pre-attention GEMM is a good example because the feature is not simply faster or slower. It depends on token thresholds, workload shape, hardware scheduling, and whether overlapping work actually improves utilization. Operators should read a knob like that as a sign to benchmark their own traffic, not as a universal speed guarantee.
All-to-all communication matters because MoE-style serving pushes tokens across devices. The model may be mathematically sparse, but the infrastructure has to move routing data, activations, and expert work at high speed. BF16 and MXFP8 support in that communication path is about bandwidth, precision, and hardware fit. A weak communication path can erase the gains of specialized kernels.
The deadlock and race fixes are even more important than the performance notes. A persistent top K deadlock may not show up in a tiny health check. An inter-CTA initialization race may depend on a particular schedule. These are production-shaped bugs, rare enough to pass casual testing, severe enough to freeze a serving path under the wrong load.
CUDA graph capture fixes sit in the same category. Graph capture assumes stable shapes, memory behavior, and configuration invariance. If max-batched token state, GPU block overrides, or memory pool settings drift outside those assumptions, the optimization can become a correctness bug. Serving stacks need guardrails that reject unsafe configurations before they become runtime surprises.
Tool call conversion is the agent-facing edge. A server can generate beautiful prose and still be unusable for agents if the non-streaming tool call path returns the wrong types. Streaming and non-streaming are often implemented through different parser paths, so both need testing. For agent workloads, structured output reliability is not an accessory to inference. It is part of serving correctness.
That is why patch releases like this deserve attention. They reveal the invisible checklist behind stable serving, kernels, communication, quantization conversion, cache loading, rope initialization, CUDA graph invariance, memory pool policy, structured output parser arguments, and hardware-specific backends. When those pieces align, the model feels like an API. When they do not, the model feels like a lab build.
For vLLM operators, the safest response is to make the patch notes into a load test checklist. Test the batch shapes that hit top K paths. Test the DeepSeek tool call mode you expose to agents. Test CUDA graph capture with the same memory and model length configuration used in production. Test cold starts that rely on compile caches. And test both streaming and non-streaming responses, because parser bugs often live on only one side.
The broader pattern is that reliability work is rarely one dramatic fix. It is a chain of small invariants holding at the same time. The kernel has to compute correctly. The communication path has to route efficiently. The cache has to initialize once and load predictably. The memory pool has to respect limits. The parser has to return types the caller can trust. When an inference server fails, it usually fails because one link in that chain broke under a production-shaped workload. The broader lesson is that serving a new frontier or open-weight model is not one feature. It is a stack: model config, tokenizer behavior, attention backend, Mo routing, communication precision, quantization, compile cache, CUDA graph capture, memory pool policy, structured output parser, tool call converter, and hardware-specific backend. vLLM version 0.20.1 is valuable because it shows that stabilization work openly. Builders should read these patch releases as a map of where their own inference deployments can fail.
The setup advice is to keep a serving acceptance test that looks like real agent traffic. Include one plain completion, one structured output request, one streaming tool call request, one non-streaming tool call request, and one long context batch that exercises cache and graph capture settings. Then run it after every serving upgrade. If only the plain completion passes, the model server is not ready for agents yet in real production agent use today under load. There is a final builder lesson here. Do not wait for incidents to decide what your timeout, queue, checkpoint, and parser policies mean. Write them down, test them, and expose them in the tools operators already use. If a voice queue closes, a graph node times out, or an inference parser rejects a tool call, the system should say which policy fired and what state was preserved.
That is the difference between an impressive agent stack and a maintainable one. The maintainable stack has limits before overload, typed errors before mystery failures, checkpoints before process death, and structured progress before users start guessing. The technologies in this episode are different, but the engineering posture is the same: make the runtime boundaries explicit enough that humans can operate them. For episode notes and source links, visit Toby on fitnesstech.com.
That is it for OpenClaw Daily. Thanks for listening, and we'll be back soon.